Hey everyone, we're getting down to the end of the quarter now, and we're starting our final chapter. So this is chapter 13. Now, we saw that curves in R2 can be expressed by parametric equations. Right, so that's x equals f of t, y equals g of t. Maybe there's some bounds here, maybe t has to be between some numbers a and b, maybe it doesn't. Now, we can do the same thing in R3. So we can do the same, or the same idea, let's say. So the same idea holds in R3, meaning that we can have a curve described by three parametric equations now, right? So curves in R3 are given by. So now what we'll have is x equals f of t, y equals g of t, and z equals h of t. So these are the parametric equations of a general curve in R3. Now, it's actually useful to rewrite it in both dimensions 2 and dimension 3, to write this in vector form. So it is useful to express these in vector form. And so in the two-dimensional case, what we would have is we would have r of t equal to, and what we'll do is we'll put the x coordinate, the f of t, in the first spot, and the g of t in the second spot. So remember, a vector is just a way of keeping, arranging information here. And so what we'll have then is a vector equation, or sorry, a vector formula, vector function, right, that describes the curve. In three dimensions, it would be r of t equal to f of t, comma g of t, comma h of t. And you should be able to go back and forth between the parametric form, right, and the vector form. Also, physicists like to use the IJK notation, and so equivalently, r of t equals f of t times I plus g of t times j. In the three-dimensional version, it would be f of ti plus g of tj plus h of t times k. So once again, you should be able to go back and forth between the vector form using the IJKs, the angle brackets, and the parametric form. They all give the same exact information. Now, so let me just draw the picture in R3. Here's what we have when we write it in vector form right now. So we have some curve, right, in R3. And so for each choice of t, what we get, or the way you can think of this, is we have the vector r of t. And if you draw its position vector, then what you have is the tip of the vector is pointing to a point on the curve, right? And each time you change t, you get a new point on the curve, right? If I gave you, let's say, s, right, then, so let's put that up here. So that's r of t. And then if I chose, say, s, maybe s gives us that point right there. So there's r of s. R of t is called a vector valued function. So what that means then, the input is t, right? It's just a real number, but the output is a vector. So the value, the output of the function, is a vector, so we have a vector valued function. Now, just as when we did parametric equations in 2 dimensions, now we've got it in either 2 dimensions or 3 dimensions. We typically, or very often, instead of using the parametric form, we will use the vector form. But no matter what, when we have a curve in space, we can view all of those points together as the path of some particle, right? So if we view the curve as the path of a particle, then at each, you can think of t as time now, and for each t, we have a new position, and so r of t is called the position of that particle. So then r of t is the position vector, or just position at time t. So, right, so we can interpret r prime or r of t as position. Typically, drawing a curve, a parametric curve in 3 dimensions is going to be difficult. We'll look at a few examples, but overall it's difficult. All right, so here's just an explicit example. So r of t equals cosine of t times I plus e to the t times j plus 1 plus t times k. Right? So each time we choose a new t, it gives us a new vector at R3, and the tip of that vector is pointing at a new point on the curve. And so, for example, when t equals 0, we have r of 0. The position at time 0 is going to be 1i, so I, plus j plus k. So this tells us then that this curve right here, and I have no idea what this curve looks like. It's a complicated curve. But I do know that it passes through the point 1, 1, 1. Right from there. Here's a famous example. It's called the helix. So we have r of t equal to, I guess I'll use the ijk. So cosine t times I plus sine t times j plus t times k. Now, if you note, the I and the j components, right, the cosine t and the sine t part, if we just ignore that part, right, this lies on a circle, right, that's the parameterization of a circle of radius 1. And so, here's the picture, here's the idea of what this helix looks like. Now notice, if we throw in the third component now, the t part, that tells us that it's going to be going up in the z direction. And so the helix then lies on a cylinder of radius 1. Let's put the axes, right, there's my y-axis right there, the x-axis coming out of the board. So this helix actually, what it's going to do is going to wrap itself around. Here's my x-axis, so it starts like this. And it goes like that. And of course, it does wrap. So what it is, a helix is a spiral, right? It stays along, stays on the surface of this cylinder right here. As t increases, the z component, the third component, increases, so that's making it go up, 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 up. So what you get is a spiral shape. That's the helix. There's a couple of sort of famous, or not famous, I should say standard parameterizations that you're going to need to know. Hey, guess what? We've already done a parameterization. Line, right? So here's another example. Lines can be written as r of t equals, say, r0 plus t times v. Right? There's a vector valued function, and the picture, of course, looks like this. Here's our line. There's our 0, and each time you choose a new t, oh, that should be r of 0. Let me fix this. Let's do this better. Sorry, I have a limited space here. There, r sub 0 is r of 0. And then, in general, each time you take a new t, it spits out a new point. So the line through space is a curve, and it's given by this vector valued function right there. Here's one that you're definitely going to need in the future, especially if you go on. Well, I should say, you will need this if you're going on to Math 241, right? Parameterizing line segments. So let's say that we have 2 points. And this will work in both R2 and R3. Let me just do it in R3. Well, actually, no. You know what? Let's do this a little. Let's do it in general, so I don't have to write it twice. So let's say that I want the line segment from P to Q, right? And I'd like a parameterization, a vector valued function that describes this, right? The parameterization. Here's one that works, and in fact, it turns out that there are more than one. There's more than one correct way to do that, but here's my preferred way to do it. This right here is a parameterization of the line segment. So what you do is you take the point P and put angle brackets around it, write it as a vector. Same thing with Q, write angled brackets around it so it's expressed as a vector, and then this will give us a parameterization of the line segment from P to Q, right? As long as you keep T going from 0 to 1. So when T equals 0, notice what you get. You get P. When T equals 1, this part's gone, and you get Q, right? And so when T equals 0, you're at P. When T equals 1, you're at Q. When T is in between, you're somewhere along that line segment as you go. Right, so for example, parameterize the line segment. From 1, 2, 3 to -1, 0, 4. So here's my P, here's my Q. And so what we get is R of T equals 1 minus T times 1, 2, 3 written as a vector, plus T times -1, 0, 4 written as a vector. There's Q. And then if you want, you can join it all together into a single vector. It's sometimes useful, sometimes not. So 1 minus 2t, 2 minus 2t, 3 plus t. And remember, we got to go between 0 and 1. Now, given some parameterized curve, so given r of t equal to it looks like your book for the, I was just checking because we just switched books, and so I just want to see how they, looks like, oh no, they go back and forth between the angle bracket version. Yeah, but they mostly use I, J, and K. They use a little bit of the angle bracket, but mostly I, J, and K. So I'll stick with I, J, K notation. So R of t equals F of t times I plus G of t times K plus H of t. Oh, no. Sorry, that's a J there. Times J plus H of t times K. Now, we can define the limit, or we can compute the limit. All right, so we have some arbitrary vector-valued function here that you can think of some curve. We can compute the limit in the obvious way. The limit as t approaches, let's say, a of r of t is going to be computed by computing the individual limits right here. So it's equal to, in parentheses, limit as t approaches a of f of t times I plus limit t approaches a g of t times j plus limit t approaches a h of t times k. All right, so for example, let's say that we've got r of t equals, so it's going to be t minus, or t squared minus 1 times I plus t squared minus 1 over t minus 1 times j plus cosine of pi t times k. Then, if we want to compute the limit as t approaches 1 of r of t, we compute the limits of the individual functions. Okay, so as t approaches 1, well, that's going to approach 0, so it's going to be 0i. As t approaches 1 here, cancel and factor, we're going to get t plus 1, so that'll be 2j. Plus, let's see, cosine, oh, actually it's minus, right, because cosine of pi is minus 1, so it'll be minus k. All right, so that's the limit of our vector value function as t approaches 1. Once we have the notion of limit, that allows us to define what it means for a function to be continuous, a vector value function. So, r of t is continuous at a if the usual thing, right, the limit as t approaches a of r of t equals r of a, right? It's exactly the same definition that you learn when you're doing calculus, Calc 1, let's say. Okay, so now we're going to start talking more about the calculus of parameterized curves. So suppose we have a curve. So suppose we have a curve given by the parameterization, so the vector valued function r of t. And let's say we've got some bounds. It's not necessary, so let's say on a less than or equal to t, less than or equal to b. So let me draw the picture here. So in R3, we've got some curve. You can think of that point right there, that corresponds to t equals a. All right, so there's, that's the vector r of a. I don't want to crowd my picture too much, but this would correspond to r of b. Oops, that should be an r of a right there. In fact, let's not crowd the picture. The position vector corresponding to that point is r of a. The position vector corresponding to this point right there, that would be r of b. Now, let's take the position vector corresponding to some point on the curve. So that's going to be some r of t. And then I want to think about a point on the curve right here that's obtained by advancing a little bit, let's say by an increment of h, which would mean that this is r of t plus h. Now, if we joined those two vectors right there, this vector right here is r of t plus h minus r of t. And maybe you can see where I'm going with this now. What I want to do is take the limit. I want to get closer and closer and closer. And this is going to allow us to define the derivative. So, we define, well, I'll just say, well, let's take the derivative. So d dt of r of t, which we often write as r prime of t, by definition is going to look exactly like the calculus definition. So what I want to do is I want to get closer and closer and closer, and this should measure the way that the curve is, I can't say sloping, but the way you would be pointing, the direction that you would be. If you were a particle traveling along this curve at t, what would your actual direction be? Well, that would be described by a vector. And so it would be the limit as t approaches, or not t, sorry, as h approaches 0 of f of t plus h minus f of t divided by t. Oh, yeah, not f, r. And so that vector right there is r prime of t. Now, there's a little bit of terminology here. So the vector r prime of t is the tangent vector to the curve C. I don't know if I actually called this capital C, but let's call it capital C. To the curve C at t. Now, if we actually view r as the position of a particle, so if r of t is the position of a particle, then r prime of t we will usually write as v of t is the velocity. All right, so it measures the direction, it measures how fast and the direction that you're traveling at a given moment. If r prime of t exists and r prime of t is not equal to 0, the 0 vector here, then we say that the curve is smooth at that point. Right, so then then C is smooth at t. So this is a little bit of terminology. One more thing, the tangent line to C at t is, so remember now, if we're working in R3, the or any line, right, needs a direction vector and a point that it passes through. So then, so the tangent line to C at t is the line with direction vector r prime of t through the point r of t. And I'm cheating a little bit here when I write r of t because r of t really is a vector. So it's really the point that the tip of r of t is at, right? A little bit more here. So the speed is the magnitude of the velocity. And the acceleration, I think everyone can guess this. So let's say a of t, which equals v prime of t, is acceleration. So I want to just get all of this down, and we'll come back and pay more attention to the acceleration a little later. Oh, yeah, one more piece of terminology. So the vector which we write as capital T prime of t, and it is r prime divided by the length of r prime, right? So, r prime. What does this do? It gives us a unit vector. This is called the unit tangent vector. Now, we defined the derivative, right, r prime, in terms of a limit. And you do the same thing in Calc 1, and you have to, you do a few examples of calculating, and then you learn formulas for computing it. We are never in this class, going to compute a derivative of a vector valued function using the definition. So, computing r prime of t, that's easy. So if, and I'm going to write this in vector form now, so if r of t equals in angle, or I should say in angle bracket form, f of t, g of t, h of t, then to compute r prime of t, it's easy. All you do is take the derivatives of each of the components. All right, so r of t is going to be f prime of t, comma g prime of t, comma h prime of t. All right, so computing the derivative, right, is the simple process of computing each of the individuals. Okay, so let's try an example. So let's let C be the path of a particle, or the particle with position r of t equals cosine of ti plus sine of tj plus t times k. Remember, this one is the helix. All right, so this gives us the position of some particle at time t. And what I want to do, so there's three parts here. So first, let's find r prime of pi and t prime of pi. And then part B, I want to find the equation of the tangent line. Through the point minus 1, 0 pi. Okay, so what we have here is the helix, and let me just remind you, so remember the helix, it's kind of easiest to draw for me if I draw it on a cylinder. So okay, so if we start here with t equals 0, what happens? Well, so we want to find r prime of pi. So imagine now, as you go around, so there's the negative axis coming around the back. And I made it a little too cockeyed here. Sorry, I want to ask a question. I want to sort of interpret this geometrically before we actually do the computation. Okay, so here's my cylinder. I just didn't like how I drew my x-axis. Right, it needs to be a little more straight. And so now I'm going to start here. I don't like this. Sorry. In fact, I don't even know if I want to draw my x-axis. Yeah, you know what? Forget the x-axis. I'm just going to draw the picture of the helix without the axes. So I want you to think of it this way. So you've got a particle, you're going around in this spiral, right? So now you start like this, and you go around, and you keep going around. Okay? So now at t equals pi, you've gone exactly half of a revolution, so you're going to be right in the back. So what I want you to do is point in the direction of r prime of pi. So think about that for a minute, and in your head now, think about what's happening as you go around, right? R prime of pi is going to be pointing in that direction, right? So our answer should match this idea right here, or that direction. Okay, so first let's compute r prime of t. That's going to be, so remember, you take the derivative of each individual component, so that's going to be a cosine t, no it's not, it's going to be minus sine t times I plus cosine t times j plus k. So, and for me, it's so much easier to think in the math way rather than the physics way with angle brackets. So minus sine t, cosine t, 1. And so now we want r prime of pi. And so that's going to be, let's see, the sine of pi is 0. Cosine of pi is minus 1. And so there's our vector. So what is that saying? There's no direction there's no contribution in the x direction, but the y direction is a -1 and the z direction is a -1. So what we get is a tangent vector that's doing that. It's pointing in that direction, exactly what we expected. The magnitude of r prime of pi is going to be square root of 2. And so the unit tangent vector t, capital T of t, that's equal to 0 minus 1 over root 2, 1 over root 2. And you can write this in IJK notation if you want, but I don't know. It's so much easier for my mind to picture it in the angle bracket notation. Okay, so now we want the equation of the tangent line through -1, 0, pi. So that corresponds to when t equals pi. So for part B, -1, 0, pi. Sorry, this was part A here, huh? So for part B, -1, 0, pi corresponds to t equals pi. And so our direction vector is going to be r prime of pi, which is, let's see, r prime, oh, I already did that, good. R prime of pi, which is 0, -1, 1. It passes through this point, -1, 0, pi, and so the equation, let's do parametric equations of the line. X is equal to -1, y is equal to 0 minus t, so that will be a negative t, and z is equal to pi plus t. Right? Here's our direction vector. There's the point that it passes through. If you have that, you can just write down the equations, parametric or vector equation of the line. Okay, one more concept to include here. Right, so we learned about derivatives of vector valued functions. You can also compute antiderivatives of vector valued functions. So a vector valued function, let's call it capital R of t, is an antiderivative of r of t if the usual thing, capital R prime of t, is equal to little r prime of t. In this case, we use the usual antiderivative notation, so we would write antiderivative of little r of t dt equals capital R prime of t plus c, where now c is a vector. Right? Now, because we know how to compute derivatives, that tells us that we know derivatives of vector value functions. That tells us how to compute antiderivatives of vector value functions. So computing antiderivatives goes like this. So let's say if r of t is equal to f of t times I plus g of t times j plus h of t times k. Then, to compute the antiderivative, what you do is compute the antiderivatives of each of the functions individually, so that's going to be the integral, or antiderivative, f of t dt times I plus antiderivative g of t dt times j plus antiderivative h of t dt times k. Now notice, when you compute an antiderivative of a function, you get a constant of integration. So there'd be like a little c1 here, a little c2 here, and a c3 here. And that, so there'll be a little c1, there'll be a little c2, there'll be a plus little c3 here. And so this c vector right there is exactly c1 comma c2 comma c3. All right, that will be your constant of integration. It will be a vector. And you can do the same thing if there's we can do definite integrals also. So so let's say similarly for definite integrals. So the integral from a to b of r of t dt. I just want to get this down. I think everybody knows what's going to happen. Use this formula, but put limits of integration on each of those. So it'll be integral from a to b f of t dt times I plus integral from a to b g of t dt times j plus integral a to b h of t dt times the vector k. So let's try a couple examples here. So let's do the integral, or the antiderivative, of cosine t times I plus e to the tj plus t squared k dt. So look at what our formula tells us to do. Compute the antiderivatives of each of those pieces individually. So that's going to be sine of t plus little c1 times I plus e to the t plus c2 times j plus t cubed over 3 plus c3 times k. Now, if a problem just asks for an antiderivative, you can leave it just like this. But there are times when we want to sort of pay attention to who these constants are, and it can be helpful to separate them off. So this answer is acceptable, but so is this one. Sine t I plus e to the t j plus t cubed over 3k plus, and I know this is going to look a little bit weird. I like it better in angle brackets, in angle bracket notation, plus c1i plus c2j plus c3k. All right. Oh, yeah. This is my c, my vector c right there. So there will be times when it'd be helpful to split the constants of integration off into its own individual vector. Let's try one more example. We'll do a definite integral here. So let's do the integral from 0 to 1 of ti plus t squared j plus t cubed k dt. All right, so that's going to be t squared over 2 from 0 to 1 I plus t cubed over 3 from 0 to 1 j plus t to the 4th over 4, 0 to 1 k. Plug in the limits of integration now, and what we get is a 1/2 I plus 1/3 j plus 1/4 k. Okay, so that's a good place to stop. And so we will see you next time, okay?